Good morning. Today we are going to discuss about the kinetic theory of gases. Kinetic theory of gases. So first, gases also can expand on heating. They have two coefficients of expansions. One is volume coefficient. Second one, pressure coefficient. Solids having three coefficients of expansion, alpha, beta, gamma. Liquids having only volume coefficient, that is gamma A, gamma R. But gases having volume coefficient and pressure coefficient, because when temperature increases, both volume and pressure can increase. At a constant pressure, we define volume coefficient alpha, that is Vt minus V0 by V0 into d per degree centigrade. At a constant pressure, the ratio of increase in volume for the rise of 1 degree centigrade temperature to its original volume at 0 degree centigrade. Similarly, pressure coefficient beta defined as at a constant volume, the ratio of increase in pressure Vt minus V0 by V0 into d per degree centigrade. And for all the gases, volume coefficient and pressure coefficient are equal, and that is 1 by 273 per degree centigrade. For all the gases, volume coefficient and pressure coefficient are equal, that is 1 by 273 per degree centigrade. Gases having two coefficients of expansions and the relation between them, alpha is equal to beta. Okay. One more formula for alpha is V2 minus V1 by V1 T2 minus V2 T1 per degree centigrade. Suppose at the temperature of T1, volume of the gas is V1. At a temperature of T2, volume of gas is V2 under constant pressure. Then volume coefficient alpha is equal to V2 minus V1 by V1 T2 minus V2 T1. Similarly, pressure coefficient, another formula P2 minus P1 by P1 T2 minus P2 T1 per degree centigrade. Okay, and all gases alpha beta are equal. Okay, next about Boyle's law. Boyle's law. At a constant temperature, the pressure of given mass of gas is inversely proportional to its volume. At a constant temperature, the pressure of given mass of gas is inversely proportional to its volume. Therefore, PV is equal to constant. At a constant temperature. Therefore, this constant depends on mass and nature of the gas. PV is a constant. Therefore, we can write P1 V1 is equal to V2 V2. And this constant depends on mass and nature of the gas. This constant value depends on mass and nature of the gas. Next, if you plot a graph by taking pressure and volume, we can get a parabola curve. P is inversely proportional to V. And Boyle's law holds good at high temperature and low pressure. High temperature and low pressure. Boyle's law holds good at high temperature and low pressure. Boyle's law holds good at high temperature and low pressure. And if you plot P 1 by V graph, that is a straight line. That is a straight line. P 1 by V graph is a straight line. And one more graph, PV and V. PV and V graph, it is a parabola, a straight line, parallel to x-axis. Okay. Next, one problem. Pressure of gas increased by X%, then pressure increases, volume decreases, then volume of gas decreases by 100x by 100 plus x percent. In percentage, that is some large percentage. Pressure increased by x percent, then volume decreases by 100x by 100 plus x. Volume should decrease, so denominator should be more, 100 plus x. Like that, you remember. Inversely proportional is there, then you can apply this formula for other chapters also. Pressure decreased by x percent, then volume increases by 100x by 100 minus x. If you decrease the pressure, volume should increase. Volume of the gas increased by 100x by 100 minus x percent. These two formulas important formulas. For example, small changes means volume increased by 2%, pressure decreased by 2%. Not a problem. But large percentages, we have to apply these formulas. So, one problem, pressure is decreased by 20%, then volume increases by 100x by 100 minus x, because volume should increase. So denominator should be less, 100 minus x. So 100 into 20 by 100 minus 20. That means 100 into 20 by 80. So 4 times, so 25%. 25%. Okay. Next, pressure, atmospheric pressure. What is atmospheric pressure? Pressure due to atmosphere is called atmospheric pressure, that is 76 centimeters of Hg. Actually, formula Hg, that is 76 into 10 power minus 6 into density, 13.6 into 10 power 3 into G, 10. So, approximately 1.02 into 10 to the power of 5 Pascal. This is atmospheric pressure. In the barometer, if you use mercury, we can get a height of 76 centimeter. If mercury replaced by water, the height is 10 meters of water. Atmospheric pressure is equal to 10 meters of water. If other liquid is, you want to take other liquids also, if you know the density, HDG formula, 2 times you have to apply, you have to calculate the other liquid height in the barometer. So if you take water instead of mercury, the height is 10 meters of water. Atmospheric pressure constant to 10 power 5 Pascal, but that is expressed in terms of mercury, 76 centimeters of mercury or 10 meters of water. Now one problem, there is a lake, one air bubble from bottom to top reached, its radius is doubled while coming from bottom to top. Calculate the depth of the lake. What is the depth of the lake? So temperature constant. Let us assume temperature constant or in isothermal condition. So P1 is equal to P2 V2. First of all, volume is V for this one. For this one, radius doubled and volume increased by 8 times, 8V. Volume V is equal to 4 by 3 pi r cube. So here volume is 4 by 3 pi 2r whole cube. So 8 times increases 8V. Volume of the bubble 8 times increases. So here pressure is atmospheric pressure capital H plus water liquid pressure H. So H plus H into volume V is equal to, here pressure is only atmospheric pressure into volume 8V. So VV cancel, H is equal to 7 capital H. Capital H means atmospheric pressure in terms of water, that is 10 meter. So 7 into 10 meter, that is 70 meter. The depth of the lake is 70 meter. The depth of the lake is 70 meter. Suppose in a mercury tub, if we take mercury tub, here what is the depth of the mercury tub? H value you have to take 76 centimeter. 7 into 76 centimeter you can get answer. Answer is in centimeters. If mercury tub, if it is a mercury tub. Here it is water lake, that's why depth of the lake is 70 meter. Next, Boyle's law completed. Boyle's law holds good at high temperature and low pressure. High temperature and low pressure, Boyle's law holds good. Next, Charles' first law. Charles' first law states that at a constant pressure, volume of gas is directly proportional to absolute temperature. Absolute temperature means temperature is in Kelvin scale. Therefore, V1 by V2 is T1 by T2. And if you plot a graph, volume and temperature, we get a straight line graph, VT graph. Next, Charles' second law or Game's law. Charles' second law. At a constant volume, pressure of gas is directly proportional to absolute temperature. At a constant volume, pressure is directly proportional to absolute temperature. Therefore, T1 by T2 is T1 by T2. Therefore, if we plot a graph by taking pressure and temperature, then is also straight line. Directly proportional means a straight line. Inversely proportional means a parabola. Next, one important problem. Temperature is increased by 1 degree centigrade. Pressure of the gas increased by 0.1%. Pressure increased by 0.1%. Temperature increased by 1 degree. Calculate the initial temperature of the gas at a constant volume. At a constant volume or in a closed vessel. Closed vessel means volume constant. Temperature increased by 1 degree, pressure increased by 0.1%. Therefore, volume constant, so we can apply P1 by P2 is P1 by P2. So, initial pressure is 100, final is 100.1. Because 1% increase means initial value you have to take 100. So, let us take initial temperature is T, final temperature increased by 1 degree centigrade or 1 degree Kelvin same. So, increased by 1 degree. So, now we cross multiply 100 T plus 100 is equal to 100.1 T. So, subtract this one, 100 is equal to 0.1 T. Therefore, T is equal to 1000. 0.1 coming to denominator, then 1000. Capital T 1000 Kelvin. Or 270 minus 273, 727 degrees centigrade. The temperature, initial temperature of the gas is 727 degrees centigrade or 1000 Kelvin. Next, according to Boyle's law, P proportional to 1 by V. According to Charles' law, P proportional to capital T. Combining these two, we get P proportional to P by V. Therefore, P is equal to some constant R into V by V. Therefore, PV is equal to RT. We get a gas universal gas equation. PV is equal to RT for 1 mole. For n mole, PV is equal to nRT. PV is equal to nRT. Where capital is called universal gas constant, that is 8.314 joule per Kelvin per mole. Joule per Kelvin per mole. Okay. So PV is equal to nRT. N is the number of moles. N number of moles. N is equal to mass of gas by molecular weight formula. N is mass of gas by molecular weight. Okay. So now the equation becomes PV is equal to M by M RT. That is PV is equal to M into capital by molecular weight is called gas constant small r into B. So small r is gas constant. Capital R is universal gas constant and its value same for all gases, but gas constant is different for different gases. Small r units, small r gas constant units joule per kg per Kelvin. Joule per kg per Kelvin. Its value is not fixed. It is different from different gases. What is the relation between small r and capital R? Small r is equal to capital R by molecular weight. This is the relation. Small r is equal to capital R by molecular weight. We can see one problem. One open vessel is there. A open vessel means pressure constant, volume constant. Some mass of gas is there. Mass of gas is there and temperature T. Now temperature is increased. Temperature increased. Or it is heated. Heated means some gas is going out. Some mass of gas is going out. So initially temperature is at 27 degrees centigrade. Now it is made 127 degrees centigrade. Calculate mass of the gas expelled. Mass of gas expelled. PV is equal to MRT. Therefore, MT is variable, MT constant. Because PV and P pressure constant, volume constant, open vessel means. And small r is gas constant, that is also constant. MT constant, M1 T1 is equal to M2 T1. M1 T1 is equal to M2 T1. What is initial mass? Initial mass of gas they given 2 grams. Temperature 27. And the temperature is increased to 127. Find the mass of gas expelled. So initial mass 2, temperature T1 means 273 plus 27, 300 is equal to M2, mass of the remaining gas in the vessel, into T2. 127 means 400 degrees centigrade. 127 plus 273, 400. Now 2 zeros cancel. So 2 1s, 2 2s. So M2 is equal to 3 by 2 into 1.5 grams. The mass of gas remaining in the vessel is 1.5 grams. Then what is the mass of gas expelled? M1 minus M2 how much? 2 minus 1.5, that is 0.5 grams. The mass of gas expelled is 0.5 grams. Mass of the gas expelled from the vessel is 0.5 grams. Okay? Next, it is a closed vessel, cubic vessel, and 1 mole of gas is there, and molecules are moving and they are colliding the walls and exerting pressure on the walls, and RMS velocity of the gas molecules V bar. RMS velocity of the gas molecule is V bar. Then the pressure exerted on the walls, pressure of the gas P is equal to 1 by 3 rho V bar square. Rho means the density of the gas. Rho is the density, mass by volume, density of the gas. So this is one formula. We have derivation for the both purpose. So kinetic theory of gases. Gas molecules are moving in all directions. They exert the pressure on the walls of the vessel. Pressure exerted P is equal to 1 by 3 rho V square. Okay. Then pressure P is equal to 1 by 3 rho mass by volume into V bar square. V bar is velocity of the gas molecules. RMS velocity square. Then we multiply by 2, divide by 2. Half mv square, the kinetic energy. So that is 2 by 3 E under P by V. Half mv square is E. So 3V denominator. So we take V that side. PV is equal to 2 by 3 E. Therefore, kinetic energy of the gas, 1 mole of gas, E is equal to 3 by 2 PV, that is equal to 3 by 2 RT, because PV is equal to RT for 1 mole. So therefore, kinetic energy of the gas of 1 mole 3 by 2 RT. So kinetic energy of the gas depends on the temperature only. As the temperature increases, kinetic energy of the gas increases. So 3 by 2 RT. One mole contains Avogadro number of molecules. Therefore, kinetic energy of one molecule. One molecule. So it is for one mole. For one molecule, kinetic energy of one molecule is equal to E dash is equal to 3 by 2 RT by Avogadro number. By Avogadro number. Because one mole contains Avogadro number of atoms. So kinetic energy of one atom. One atom. Therefore, kinetic energy of an atom is equal to 3 by 2. Capital R by Avogadro number is called Boltzmann's constant into T. So 3 by 2 kT. Kinetic energy of one gas molecule is 3 by 2 kT or kB into T. kB is called Boltzmann's constant. Boltzmann's constant. Capital R by Avogadro number is called Boltzmann's constant. You know now, Avogadro number 6.023 into 10 power 23. Capital R 8.314. Therefore, Boltzmann's constant. Capital R by Avogadro number. So 8.314 divided by 6 into 10 power 23. So approximately 1.6 into 10 power minus 23 joule per Kelvin. Boltzmann's constant. Because capital R units joule per kg, joule per Kelvin per mole divided by for this Avogadro number per mole, the 1 by mole. So mole cancel, we get joule per Kelvin. Unit joule per Kelvin for Boltzmann's constant. So in a gas, molecules are in random motion. They have RMS velocity, root mean square velocity, and we can take their average velocity also. Average velocity of gas molecules. Average velocity V average is equal to root of 8 RT by pi m. 8 RT by pi m formula. Average velocity of the gas molecule 8 RT by pi m. And RMS velocity, root mean square velocity. V RMS is equal to root of 3 RT by m. RMS velocity of the gas molecule root of 3 RT by m. And the most probable velocity, V mt, most probable is root of 2 RT by m. Root of 2 RT by m. So gas molecules having RMS velocity, average velocity, most probable velocity. And in these RMS velocity is more than most probable average velocity than most probable. We can check it. So here T by m constant, R also constant. Root 8 by pi. Root of 8 by pi. Here root 3. Here root 2. What is root 2? Root 2 means 1.414. Root 3 1.732. Root 8 by pi. So 8 by 22 by 7. 8 by 22 into 7. So 56 by 22. So approximately 44. So 2 point something, 2.5. So root of 8 by pi is root of 2.5, more than this, less than this. So it is in between them, approximately 1.6 something. So V RMS is greater than V average greater than V most probable velocity. Most probable velocity. Suppose 5 to 6 values of velocity of the gas molecules are given. Which one repeated more times? Out of 10 values, suppose one value repeating, that is taken as the most probable velocity. That is the most probable velocity. Next, mean free path. Mean free path. Mean free path is represented by lambda. That is the average distance traveled traveled by the molecule before collision. Average distance. Suppose it is a molecule is colliding different molecules. So it will travel certain distance collide and travel another distance collide. Then what is the average distance traveled? So that is called the distance of mean free path. That is 1 by root 2 formula 1 by root 2 pi m square d. N is the number of particles per unit volume. N is the number of particles per unit volume. D is the diameter of each molecule. So root 2 pi m square d formula. So number of molecules inversely square of lambda mean free path inversely proportional to square of the number of the particles per unit volume. D is the diameter of the each molecule. D is the diameter of the each molecule. So this is about the kinetic theory of gases. And Vrms is equal to root of 3RT by m. And the velocity of sound in the gas is equal to root of gamma RT by m. Velocity of sound in the gases. Therefore, the ratio of these two, Vrms by V sound, is equal to root of 3 by gamma. One important concept. And Vrms is equal to root of 3RT by m. Therefore, V directly proportional to root 3. V1 by V2 is equal to root of T1 by T2. V1 by V2 is root of T1 by T2. At what temperature? One problem. At what temperature velocity of sound is double that at 0 degree centigrade? At what temperature velocity of sound is double that at 0 degree centigrade? At what temperature velocity of sound is double that at 0 degree centigrade? So here initial temperature 0. What final temperature how much? So V1 by V2 is root of T1 by T2, that is V by 2V. At what temperature velocity of sound double or RMS velocity of the gas molecule double? So this formula valid for gases also, gamma RT by m. So V directly proportional root to T for gas. Velocity of sound. Velocity of sound is directly proportional to square root of absolute temperature. One concept. RMS velocity of gas molecules is also directly proportional to absolute temperature. And then root of initial temperature 0 degree centigrade, final temperature we have to calculate. So 0 degree centigrade means 273 by capital T. So we will cancel, squaring on both sides 1 by 4 is equal to 273 by T2. Therefore T2 is equal to 273 into 4. So for 3 is 12, 4 7 is 28, 29 to 8 plus 2 10, 1092 Kelvin. At a temperature of 1092, we get a velocity of sound will be doubled that at 0 degree centigrade, or 1092 minus 273. So subtracting 9 and here 8 minus 7, 1, 819. So 819 degrees centigrade. One more value in centigrade is 819 degrees centigrade or 1092 Kelvin. Same question, at what temperature velocity of sound become half that at 0 degree centigrade? velocity of sound become half. So here calculation is important. V by 2 is equal to root of 273 by t2. Because velocity of sound become half. We cancel. So squaring on both sides, 4 is equal to 273 by t2. Therefore t2 is equal to 273 by 4. So 4 6s 24, 6 33, 4 8s 32, 1.25, 68.25 degrees Kelvin. And then what is the value in Kelvin scale? So 68.25 minus 273. How to subtract? Okay. So if you are subtracting big value from small value, subtract small value from big value, then put to minus. So that means 273 minus 68.25, subtract, after that you can put a negative sign. So 0, 0. So 10 minus 5, 5. So here 9 minus 2, 7.75. And here 2, 12, 12 minus 8 is 4, 0, 2. 204.75. So that is equal to minus 204.75 degrees centigrade. Important model, important problem. Many of them make subtraction wrong. So at what temperature velocity of sound is half that at 0 degrees centigrade ante either 68.25 Kelvin or minus 204.75 degrees centigrade. So this is about kinetic theory of gases. Kinetic theory of gases.